Thank you all very much for coming out on this slightly sweaty day. My name's Neil Kermode. I'm one of the co-chairs of the Orkney Renewable Energy Forum. Gareth is the other chair. And just welcome you here to the July meeting. I'm really delighted that Ross Henderson from OCU has agreed to give us a talk tonight. We've had some dealings with OCU and predecessor organisation for directional drilling that have gone on at Billy Crew over the years. And having been down to see the site a little while ago, I was really impressed by what's going on and the scale of the engineering that's involved in it. As a civil engineer myself, I'm always interested in big stuff and preferably the smell of curing concrete at some point. It really does it for me. But this is a chance to really hear a little bit about the technical side of what's going on with directional drilling. I'm going to leave Ross to introduce himself. Usual plan, run for about an hour or so. Time for questions at the end. There is tea and coffee. I think we're getting down to the disposable cups now. But if anybody has got any questions, don't hesitate to say them to the end, or I assume butt in if there's a point of clarity that didn't make sense or something.
We can do butting in.
You can do butting in. Okay. We're recording this as ever, and then this will then goes up on the ERF website later on as part of the resource that's building up for technical matters which really are of interest to people involved in renewables. Final plea, if you're not an ERF member at the moment, then do feel free to join. There's some application forms at the back. And if you're a member of, or work for one of the organisations that's a business member, then you get membership anyway for free. So with that, I will hand over to Ross. The floor is yours.
Thank you very much, Neil. Thank you for the invite. So I'm going to talk about horizontal directional drilling, or HDD, generally rather than specifically, although we will cover the drills we're doing down at Warebeth, the landfall for the marine cable running across to Dounreay. We're going to be doing the landfalls at Dounreay as well. And we've got 7 onshore drills to do to get the cable under various roads and rivers between Warebeth and the new substation. So we'll cover that a little bit as well. So let's start off with the concept of HDD. Yes, you can see there. So when we're drilling, we start off with the bottom hole assembly. We start with a drill bit at the leading edge. And behind that, we have a system, or what's called here a pilot tool. And this is the bit of the assembly that does the directional for us. So when we're drilling in hard rock, do you all know what a Moino pump is? No. Okay. What about an Archimedean screw?
Yeah.
I'm a bit more familiar with that. So the usual application for an Archimedes screw is in water management. You rotate the screw and it pulls water through the screw, and you can move water between different levels for irrigation. So we use that principle, but the opposite way round. We put an Archimedes screw in the bottom joint of the drill pipe, and we pump drilling fluid down through that Archimedes screw so it spins the screw. And on the end of the screw, we put the drill bit. So the drill bit only spins when we're pumping fluid through it. And then between the power section, the Archimedes screw, and the drill bit, we put a very small angle, maybe only a couple of degrees, but that's enough to allow us to orient the drill bit relative to the axis of the drill pipe. So we can point it up, we can point it down, we can point it left, we can point it right, or anywhere in between. And if we run a real-time steering tool behind that, we know what direction we've pointed the drill bit in. So when we start off, if we want to drop angle, we rotate the drilling assembly until the bit's pointing down. We turn the pumps on so that it starts spinning the bit, and then we slide the assembly into the ground without rotating it, and the bit will drop angle. And when we've got to the inclination we're looking for, then we rotate the whole drill string from surface, and we drill a slightly eccentric hole in a straight line. And when we get to the end of the tangent section, we stop rotating, we turn the drill bit until it's pointing up, we start pumping the fluid, it spins the drill bit, and then we slide the drilling assembly into the ground, and we'll build angle until we're horizontal. And we can change the direction that we're drilling in. It's a directional drilling assembly. It's designed to go around corners. So if we hit a hard patch of rock, we'll bounce off it. And if we hit a soft patch of rock, we might drop into it. But with a real-time steering system behind us, we'll see us deviating from the intended trajectory, and we can correct for it, adjust the drill bit orientation, and through a combination of rotating the whole drill string and sliding the assembly into the ground, we can follow the planned bore path. Yeah. So once we've got a pilot hole through from entry point to exit point, we take off the steering system and the pilot hole drilling assembly, and we put a hole opener or a reamer on the far side, and we pull that back towards us. And as we pull that towards us, we add drill pipe on at the far end, and we might pull 2 or 3 reamers through. The onshore drills on Orkney will be conducted like this. We'll drill with a 6 3/4, 7 5/8 inch pilot hole, and then we'll hole open to 15 inches, and then we'll hole open to 20 inches, and eventually we'll get a 26-inch hole that's big enough for the cable duct bundle. It's slightly different at Warebeth because we're trying to minimise the amount of work we're doing out at sea, for health and safety reasons, the weather window you need to work out there, and for cost. So we're trying to do as much as we can from the onshore position. So for the landfalls, we've drilled the pilot hole and stopped just short of punch out onto the seabed. We've pulled the assembly back and we're forward reaming, we're pushing the hole openers into the ground and opening the bore up first from 12 1/4 inch pilot hole to 26 inches, and then 26 inches to 36 inches before we push the 630mm cable duct into the bore. So we're trying to do as much as we can from an onshore location there, so it's slightly different. But, yes,
Can I just ask, it's a technical question. So when you describe the angled turn, if you like,
yeah,
am I right in thinking that the hole diameter at that point will be the diameter of the drill bit, but when you straighten up, then
drills
it's a slightly bigger hole because the eccentricity has to go around the whole diameter. Is that right? So the hole almost is thin at the turns and then thicker on the straight bits.
That's correct. But once you've drilled, we very rarely drill from entry all the way to exit.
Yeah.
Every now and again, you'll stop. As we're drilling, we pump the drilling fluid down the drill string. It not only powers the downhole motor, it comes out through nozzles in the drill bit and it carries the cuttings out of the bore. If you can't remove the cuttings from the bore, you don't have a hole down there. So you're suspending those cuttings in the drilling fluid. Every time you stop, the joints of drill pipe are 9.5, 10 metres long. So every time you stop pumping to put a new joint of drill pipe on at the drill rig, you're relying on the drilling fluid to suspend those cuttings. But when you're drilling horizontally in a 12 1/4 inch bore, they've not got very far to fall before you build up a cuttings bed on the low side of the hole. So you need to keep agitating that big and putting the cuttings back into suspension. So every so often, when it starts to get a little bit tight to rotate the pipe, we'll stop, we'll come out, we'll do what we call a wiper trim and run the drilling assembly backwards and forwards through that hole, agitating the cutting, putting them back in suspension and pumping them out of the hole. That also resizes the bits of bore that might have been drilled in sliding mode and be slightly smaller. So yes, you're absolutely right with the pilot hole, but we do size the hole as we go as well. Yeah, so once we've got the hole up to a sufficient diameter, the product pipeline or cable ducts or cable duct bundle, as we have on Orkney on the onshore wells, bores, is all strung out in a single length behind us for pullback. And anybody who's been on the outer town road at Warebeth will see the pipes snaking up away over the hill. And the reason we build that in a single go is when you start pulling the pipeline into the ground or the cable ducts into the ground, you lose all the mechanical control over the bore because you're pulling the drill pipe and the hole openers out. So if you start to lose borehole integrity behind you, it's very difficult to do anything about it. So you want to get that product line in as quickly as you possibly can. So you don't have the time to stop and weld and test and pull another 10 metres and stop and weld and test. You need to pull it in as soon as you can before the quality of the bore starts to deteriorate.
Can I ask a question?
Yep.
At Warebeth, you're saying you're pulling it out to sea. So
Yeah, but pushing the pipe in.
you're pushing it rather than
rather
pulling
than
it.
pulling it in, yeah.
Okay. And then at the last stage, you're going to cut through into the seabed and let the water.
Yes. Well, once we've got the hole up to 36 inches, then we'll punch through out
Right.
onto the seabed and finish that last section of drilling off, pull the drilling assembly out and push the cable duct in.
Okay. At that point, it floods, presumably, yeah. Yeah, of course it is.
When we're pushing the duct in, yes, it's got vents in the front of it that allows it to fill. Because if you push an empty sealed pipe in, it would float in the drilling fluid and the water, and it would push itself against the high side of the hole.
Yeah.
And you wouldn't be able to overcome those friction forces pushing it in. So yes, as we push it into the ground, we allow it to fill with drilling fluid and with seawater so that it reduces the buoyancy and takes a lot of that frictional drag off the high side of the hole. So yes, it's going to be full by the time it's pushed in.
Okay. Excellent.
Okay, so I've got a wee video here that goes through stop that one. Let me start this one. So this is a wee schematic of the HDD process. And you can see that the first thing is that the only excavations we have are these small pits. We talked about pumping drilling fluid down the drill string that carries the drill cuttings back out of the bore. So these small pits at entry and exit point are the only bits that you would see on surface. So we're adding the drill pipe as we push the assembly into the ground. And we're following the trajectory. There you can see the drilling fluid coming back up the annulus, carrying all the drilled cuttings with it. That slurry, the solids laden slurry, we pump to a recycling system, and that removes the solids fraction and allows us to reuse the clean mud. So it minimises the volume of water or volume of fluid that we have on site.
So is that bentonite you use as a fluid?
Yeah. And here we can see the rotation of the drill pipe following the bore path. And as we start to deviate from the bore path, we stop. Well, that's stopping to add another joint of pipe. But the previous bit, you could see the drill pipe sliding rather than rotating. And once we get to the exit pit, we take off the pilot hole drilling assembly and we pull the hole openers back towards us. Again, pumping fluid into the bore, out through nozzles in the hole opener, and flushing the drill cuttings back to surface. So now, because we've got a larger bore behind the drilling tools, the drilling fluid is taking the path of least resistance, which would be up through the big hole rather than forwards through the small hole. So we have to have a system of management of drilling fluid to get the fluid from the exit point back to the entry point, usually done with tractors and tankers on small, relatively small bores like the onshore drills at Orkney. And then once we're back at entry point, we put another reamer on and a swivel behind the reamer so that you can rotate the reaming tool, but the pipeline or the cable duct bundle behind it doesn't rotate.
So Ross, at Warebeth, this is going to be a pushing job rather than a pulling job, is that right?
Yes, yeah.
Yeah.
So we'll show you in a few slides' time the pipe pushing system that we'll use to push the sleeve in the ground. And there you can see the reamer arriving back at surface. Remove the assembly, cut off the end of the pipes, and what you're left with is a horizontal directionally drilled sleeve beneath the roads, the rivers, railways, motorways, coastline at Warebeth, for environmentally sensitive areas.
What sort of depth are you drilling down to there? Your measured length versus TBD.
So we'll say that again. Who's talking TVD? So you've got some experience. So I'm just. So at Warebeth, we're 20 metres below surface level for the majority of the bore. For the onshore drills on Orkney, we've got a 10 metre limit,
okay,
apart from the burn of Stennis. One of the issues we have with high voltage power cables is they generate quite a bit of heat, and you have to be able to dissipate that heat into the surrounding formation, otherwise they act like a fuse and they just pop. So the electrical engineers have designed the cables and stipulated that we have to be shallower than 10 metres, otherwise the cables can't dissipate the heat into the formation. The formation at the burn of Stennis is slightly different. The thermal conductivity of the ground there is a bit less than it is at all the other onshore drills, which is why we're limited to 7.5 metres depth of cover. From a directional drilling perspective, we would always want to be as deep as we can. The deeper you go, the more competent ground you get into, the further away you are from any surface infrastructure. You don't have to worry about heave or settlement or disruption of other services. And when you're drilling an arc, going another 10, 20 metres deeper is only going to add a metre and a half, couple of metres to the length of the drill. So from our perspective, we would always want to go deeper, but the electrical engineers always want us to go shallower. So there's a compromise to meet. The marine cable is a much heavier duty cable, so we can put that in at 20 metres depth of cover.
Okay.
Okay. So a little bit about HDD history. Horizontal directional drilling started in about 1971 in America, where although they were using rigs like this set up horizontally to drive casing or auger bores through the ground underneath roads and railways, rivers, they put a pit in the ground. And we still do some trenchless work like that, auger boring, pipe jacking. You set it up in the direction you want to go in, and you just drive it through the ground and hope that it doesn't deviate from your intended line of attack. But in 1971, a guy in America called Martin Cherrington set up one of these rigs and tried to do directional drilling. Now, he didn't have any guidance systems in those days, but he put an angled drill head on and used some bent drill pipe and tried to drill 4-inch gas lines 500 feet underneath the river in California. And he was kind of successful. It took him 2 or 3 goes to get where he wanted to be, but he got there, and the industry took off fairly quickly from there. Using oil field technology, a company called Sperry Sun started to develop downhole guidance systems for the oil field that allowed you to survey where you were down the hole. And they very quickly moved to real-time guidance technology where you could see where you were going as you were drilling. So by the mid-80s, horizontal directional drilling had taken off, and it's gone through a number of iterations. There are some step changes in principally the guidance technology, but the drilling technology and the fluids management technology along the way. But from 85 onwards, it's come on leaps and bounds. So why do we directional drill? Well, obviously we're trying to avoid sites of engineering difficulty, SEDs, we call them in the civil engineering business. So that might be a road, a motorway, it might be a railway, it might be a canal, it might be a river. It might be a site of significant environmental interest. You might be trying to avoid invasive species. We do some drilling where we drill underneath Japanese knotweed, for example. We do some drills where we drill underneath ponds that have got great crested newts in them. We do quite a bit of work in brownfield sites, putting pipelines and cables underneath contaminated land. You don't want to be trenching through ground that's heavily contaminated. We did a job in Doncaster in the locomotive works where the ground is full of asbestos they used to use to lag the old steam train boilers. But by drilling beneath the asbestos, you can avoid all that environmental impact. But there are other applications as well, social implications. So rather than trenching down the high street and disrupting all the traffic and the business access, we just take a pit out at either end of the high street and drill down. We can avoid schools, we can avoid sports pitches. So there's a lot of social reasons for directional drilling. It says noise there, and I know noise is a real issue with the job at Warebeth. But again, it's a confined site. So if we can set up one site that generates a bit of noise, it's probably better than trenching, for 1.5 kilometres cross country or through an urban environment and disturbing an awful lot more people. I know that doesn't satisfy the people who are at the drill site, but noise impact is something that we're aware of. Particulates as well, not necessarily contaminated particulates, but the generation of dust from a trenching operation. When you're digging up material, taking it away to landfill and quarrying clean stone, bringing that back in and filling the trench, it's quite an environmentally, it's quite a high carbon footprint issue. Health and safety is another big factor. It's a much smaller crew than a trenching crew. And 10% of UK fatalities occur in confined space working, trench collapses, and people working in places they can't get out of when they need to. So the ability to do directional drilling without the requirement for shafts or dewatering or temporary works or shoring is a big health and safety issue. It's a faster installation, and with reduced manpower, there are reduced costs. And of course, the visual amenity for putting cables underground rather than stringing them on pylons is a big advantage. That's been particularly evident in the last few years when there's been big winter storms and overhead lines have got iced up. Particularly in northern Scotland, where they're trying to decarbonise the Highlands, people won't move off oil-fired heating and cooking systems unless they've got a reliable power supply. And if your electric power supply is supplied by overhead lines and they're down for a month every winter, you're not going to be very keen on moving to
be honest.
It's not that bad.
Don't bite, Martin. Don't bite.
I worked for the hydro, that's all. We weren't that bad.
So rig sizes. Rigs are classed by how many tons push and pull capacity they have. These are our rigs. We run rigs from the bottom end, a JT40, which is about a 20-ton rig. We use that for putting 100 mil fibre optic cables, power cables up and down city streets 100 metres at a time, going through 50 ton, 70 ton, 100 ton, right up to the DD 1100, which is at Warebeth. That's a 500 ton rig. It has the ability to push and pull 500 tons at a time. So, and that's the biggest rig in the UK. So that's as big as we get. Here's a couple of pictures. That's a mini rig doing a railway crossing in Cumbria, and there's a maxi rig. That one's at on the Caithness coastline, putting in the Magen tidal turbines. I don't know if you're aware of that scheme. We talked a little bit about guidance at the start of the presentation. So there are two principal methods of guidance. The picture on the left-hand side is what we call a walkover tool. You put an electromagnetic sonde behind the drill head and it sends a signal to surface. And by walking over the top with a locator device, you can tell where the drill bit is and how deep it is. But obviously, you can only do that if you've got surface access and you can walk above it. So the more complex systems, the wireline systems, that signal comes up a wireline in the drill pipe and gives you remote access to the guidance system. So at Warebeth, where we're drilling 1.2 kilometres out to sea, all the guidance is done from the drill cab next to the driller. The drilling bits on the left-hand side is a drill bit for soft formation. You can see this laser pointer to work. On the low side of the bit there's a flat face, and with nozzles in the top face, top of that flat face oriented to the high side, what we call the high side, that gives you that ability to push off formation and steer the drill head. The second picture there on the right-hand side is the drilling motor. That's sitting high side at the moment, so you can't really see. I'll just get a picture where you can see the bend sticking off to one side. But there's a bend in the assembly just here at the collar that allows you to orient the bits offset from the axis of the drill pipe.
Just ask, the left-hand one, is that a slightly different steering mechanism to the one you described for the hard rock?
No, the steering tool would be the same in that application.
Because
all the steering.
My understanding was that the way they steered it was when the drill bit was in one particular orientation, it pushed a bit harder.
Yeah.
And that pushed it a bit more that way.
Yeah.
And if you pushed evenly, you drilled a straight line.
Yeah.
But I thought that was how that one worked as well as the ones I remember.
Yeah. Yes, there is. You see, there's a flat face on the bottom here.
Yeah.
So that's got a flat face.
Yeah.
So when you push that, it side loads the drilling assembly and enables you to turn in whatever direction the flat face is oriented.
Yeah.
Once you start rotating the whole drilling assembly, that flat face again
it goes in a straight line, which is how I also understood that's how they worked. I didn't realise that they had this motor down the hole that you're
Yeah.
talking about for the.
Yeah, two different systems, one for soft rock or soft ground
Yeah.
and one for
All the
hard
ones I
hard
ever
rock.
did were the soft ground ones.
Mhm.
Yeah, that's it.
So the hole openers, and again, as we say, they come in different sizes. You pull a series of them through. You don't want to open that hole up in one go because you would overload the drilling fluid with drill cuttings and make it too heavy to pump. So you take it out a little bit at a time. And there's an infinite number of different styles of hole opener and drill bit available, depending on what ground conditions you're drilling through. The drilling fluids, we talked bentonite drilling fluid, so it's clay platelets mixed in a fresh water suspension. There's a little bit of viscosifier in there to help the carrying capacity, but it's quite a complex fluid. What you're trying to do is get that fluid to suspend the cuttings as soon as you stop pumping it. So it's thixotropic in effect, but you don't want it to set too quickly or too strongly, otherwise it takes too much pressure to get it going again. So it has a very quick gel strength, but a very low shear strength. If you think of it as like trying to get the ketchup out of the bottom of the bottle, and you keep banging away, and then the shear strength goes and you get all the ketchup at once. That's exactly what we're looking for. High gel strength, but low shear strength. And it also has to cool all the downhole drilling equipment. It has to lubricate the drill string, and it has to support the bore as well. So you can see in the top left-hand corner, that's the fluids technician. He's constantly measuring the viscosities, the weights, the densities, the pH, the chloride content of the fluid to make sure it's doing what we want it to do. These are the pumps. We've got some bigger pumps down at Warebeth than these ones, but these ones are oil field style cement pumps. And this is the recycling system. So the slurry laden fluid comes back to surface. We pump it up to the right hand shaker here, and that removes the coarse material from it. And the clean mud drops down into the tank and gets pumped up through a series of shakers. Now, the shakers are different sized vibrating screens, and they get finer the further down the fluid stream you work. So it gradually takes out more and more of the solids. And also on top of those, the last three here, you can see there's a series of hydrocyclones that spin the fluid, acts a bit like a centrifuge and spins the solid content out of it. So that takes the solids down to about 25 micron, which is clean fluid. The last thing we want to be doing is pumping dirty fluid and sands through our pumps and downhole, through the motor, through the steering tools, and wearing them away. So it's very important that we maintain a clean drilling fluid. Of course, you've got the butt fusion welding of the cable duct. This is what you'll see snaking over out of town road, but it'll be the same process for the smaller ducts on the onshore drills. These polyethylene sleeves, and they're heated up both ends, and then they're pushed together and they weld together, they melt together and form a single joint. So that's a picture of the drilling assembly popping up on the seabed in the kelp forest on the major jobs on the Caithness coastline at Ness of Cloyes, Gills Bay. You can see the kelp in the background there, and the drilling assembly with the drill bit coming out of the seabed. That's the pipe pusher that we were talking about. Well, that's two pipe pushers. On the left-hand side is a 50-ton pipe pusher. It's got wheels that clamp down on the pipe and rotate and push it into the ground. And on the right-hand side is our 200-ton pipe pusher. You don't want to be gripping the pipe with a wheel, so we've got much longer. They're like excavator tracks, 4 of them that clamp down on the pipe and rotate and squeeze the pipe in and out of the ground. So some of the design work we do, before we decide where we're going to drill, we need a topographic survey so that we can make sure we're going in at the right angles and building at the right radiuses and staying deep enough below any obstructions that we're trying to drill under. We do site investigation to figure out what the ground conditions are. The ground conditions dictate what sort of drilling tools we're going to need. The drilling tools dictate how quickly we can build, angle, develop radiuses in the bore and how long the job's going to take, which tells us roughly what it's going to cost. So without the site investigation, that's a very important building block in the design process. The other thing we need to know is what else is in the ground. Especially in urban environments, there's an awful lot of infrastructure already in there. Unless you know where it is, you can't avoid it. So we spend a lot of time trying to trace existing utilities and pipelines, foundations, sheet piled walls. This is what happens if you don't do your survey work correctly. You can see a directional drilling assembly going through a subway. Not the smartest thing. The design work we do, again, there are some of these items are fixed, the topography is fixed, depth of cover is often dictated by the Railway Network Rail or Transport Scotland for depths. Other things that we can play around with a wee bit, entry angles, build rates, lengths of tangent, etc., etc. So there's quite a bit of maths and geometry involved in designing an acceptable profile. This is what happens if you get your profile wrong and your drilling assembly comes up in the middle of a motorway. Again, very American, not us, not But as well as drilling in a vertical plane, we can drill in a horizontal plane. You can see here we've put 2 parallel shots in here underneath a motorway flyover, and then drilled an 85-degree horizontal turn to come out almost at right angles to the entry angle, and parallel shots. You can see here we've separated the 2 bores vertically and horizontally, so that the second shot, if we didn't manage to make the turn, there was no chance of it colliding with the initial shot we went in with. We can also stack bores. So this is an example of a job under a railway. This is between Edinburgh and Glasgow, where the easement width wasn't wide enough to put the shots in flat formation. So we've had to stack them, some of them deeper than others. And you can see the shallow ones here and then the deeper ones coming out of the ground at the back of the slide there. So we can be quite innovative with the way the jobs are put in. We talked there about depth of cover and being limited by power cable heat generation. We can put thermal grouts in the annulus to help us wick that heat away from cables. So that's sometimes a solution to enable you to go in at deeper depths than the electrical engineers might have wanted you to go in at. We can also put cementitious grouts in if we've got potential issues with very soft ground and keeping the ground stable at surface under railways, for example. This is the schematic of the Warebeth landfall, 1,200 metres long, 20 metres below the seabed, and a 12.25-inch pilot hole, 26-inch forward ring, 36-inch forward ring, and then punch out onto the seabed and push the sleeve in. So the ground that we're drilling through was a couple of that one. So feel free to pass these around. That one broke in transit. But you can see in here it's mid-Devonian siltstone. And if you look closely, you can see what they call bioturbation. There's some little animal burrows in there. And also the deformation of the layers of rock in there as more and more layers stacked up and squeezed the water out of the underlying layers. It deformed those layers slightly. So you can see the kind of density of the material we're drilling through.
Ross, just on the previous slide, the section, longitudinal section, looks like some sort of discontinuity in the geology.
Yes, it's upper strongness flagstones. There's a fault line.
Is that
about 2/3 of the way out.
right?
That faults the upper strongness flagstones up. So down. So we're staying in the top of the upper strongness flagstones all the way out. I understand from the drillers that we were making ROP.
About, so the first 700 metres was about 50 minutes per 10 metre rod, and then when we hit the fault, we got in the harder formation about 75 to 80 metres minutes a rod.
So the further out you went, once you got beyond the fault, the rock was a bit harder.
How did you find deflection off that when you went into the different section of the fault?
Sorry, say again?
How did you find, do you have any deflection in trajectory at all?
No, it stayed really well.
Yeah. Okay.
No, even either side of the fault stayed pretty similar.
Okay. No problems with cave-ins or anything like that?
No,
Or hanging
no, all good.
The other thing we always worry about drilling through fault zones is losing drilling fluid into the fault, into fractured material. But we have maintained full returns all the way through. So, yes, there's a fault there, but it probably sealed up with hydrothermal deposition or something in there to seal it up.
Well, do you come back to that fracking later on, or is this a good time to ask another fracking question?
You can ask a fracking question.
Yes. If the mud starts circulating through a crack, do you have do you just let it happen until it stops naturally, or do you have an intervention that can plug that?
Yeah. Okay. So one of the other reasons that we have these recycling units on site that minimises the volume of fluid we've got in circulation is it makes it easy to spot changes in the volume of fluid. So if we start to lose fluid downhole, we'll see it very quickly because we've only got small tanks of fluid on surface. Now, what that tells us is that the pressure of fluid that we're pumping downhole has exceeded the hole's ability to retain that fluid within the bore. So what's the reason for that fluid pressure going up? It might be that the fluid has got denser. We might have accelerated the rate at which we're drilling and loaded the annulus up with more cuttings. It makes the fluid denser. It's harder to pump. It might be that the viscosity has gone up and it's got harder to pump. It might be that some of the holes collapsed behind us and made a narrower orifice for that fluid to pass through, and that's caused the pressure build up downhole. So the first thing we do when we see fluid losses is stop, run one of these wiper trips I was talking about. Let's get all the cuttings agitated and circulated out of the hole. Let's pull back, let's regain full circulation. Now, the bentonite suspension that we use is a very weak ground. So once that's worked its way into the fissures, if you stop applying pressure on that, it's going to gel up and then it's going to seal up those fissures. So when you finish your wiper trip, you run back into bottom, 24 hours later, you may well find that you've solved all the problems. If you haven't, then there's other things we can try. We can pump what we call LCM or lost circulation material into the ground. That might be something as simple as sawdust. It might be something like mica flakes, proprietary material that we get from the drilling fluid suppliers. Worst case scenario, you might have to pump a cement pill and try and plug up any fractures. But our experience to date, having drilled 1.2 kilometres twice with full circulation, including going through the fault zones, is that we're not seeing any frack out or breakout, as we prefer to call it. On the onshore jobs where we're drilling at much shallower depths of cover, there's a risk of breakout following a path that already exists in the formation. It might be a natural fissure in the ground. It might be where somebody's had a fence pole in. It might be a site investigation bore location. We identify where these locations might be on the breakout contingency plan, and we monitor them while we're drilling. If we get any breakout, we stop drilling, we turn the pumps off, we pull off bottom, we contain it, we allow it to heal, or we pump something into the ground that's going to help it to heal. It's clay in fresh water. It's slippery, but it's not toxic. It's licensed for use on potable water wells, so it's not a problem to humans or animals or the environment. In fact, farmers quite often ask for us to spread it on their fields when we've finished with it, because it improves the water retention of chalky and loamy soils. I don't think water retention's a problem here on Orkney. But yeah, it is something that occurs, but it's something that we're very aware. If we don't maintain circulation, we're not flushing the cuttings out of the hole, so it's the last thing that we want to happen. That's the cable duct bundle for the onshore cables. There's 3 200mm diameter PE ducts, one for each phase of the power lines. There's a 125mm duct that will have 4 fibre optics subducted in it, and there's a 63mm duct that's going to have a DTS, a digital temperature sensor in there. It's a fibre optic line, again, that monitors the temperature of the power cables. So if they do begin to overheat, they can reduce the power that's flowing through the line until they can figure out what they're doing about it. So quickly,
before you move on from that, can you just go back to that picture? You're drilling with a bentonite fluid.
Yeah.
Do you somehow thicken up the amount of bentonite that's in there, or do you just let it settle and finish up with water on the top?
The bore will be filled with bentonite. When we pull the cable duct bundle in, it'll displace the volume of the duct of bentonite out at either end that we'll dispose of. But the bore the annulus around the ducts will remain filled with this weak bentonite grout. So it
doesn't settle and finish up with water on the top?
No, it's designed to suspend the cuttings.
Right.
So by the time it's gelled up, some of the cuttings will have dropped out of suspension, but the bentonite will remain in suspension.
So it's the same.
Help support the bore, and it'll stop any groundwater flows through the bore. If you're drilling up a hill, for example, you don't necessarily want to be draining the upper fields into the lower fields. No. So it seals up the annulus around the ducts.
Right, but I just wondered, because I remember with porcelain pipe ducts that were hand laid in trenches that were then filled with bentonite. You finish up sometimes with the top of the duct not full of bentonite, and I was just wondering, it's settled obviously.
Yeah.
Over time.
Yeah.
Might be 30-year-old by the time somebody do it. With JCB, and I have to go and patch it, but I just wondered if there was a different bentonite mix or something to make sure that it was full of bentonite.
Yeah, there's a little bit of viscosifier in ours that helps it helps its suspension and keeps it in suspension, rather than just pure Wyoming bentonite or Greek or Indian bentonite that might settle out.
I think there's probably more done I'm talking about. So.
Yeah.
But I'm thinking of from 40 years ago, which
Yeah.
is, and we're probably 30 years old at the time.
Uh-huh.
You know, you're probably new at the okay, thanks.
So the burn of Heddle is the first one we're going to do. It's 132 metres long. As we say, we've got 10 metres depth of cover. That's from ground level, is approximately 10 metres. So we've got 7.5 metres depth of cover beneath the stream, from the bed of the stream to centre line of the bore. You can see the dotted line in here. This is the top of bedrock in the 2 boreholes, site investigation boreholes we've had done either side of the crossing. So we're assuming top of bedrock runs between those 2 points. We won't be far off there, I don't think. And you can see the ground conditions that we're drilling in. It's pretty solid rock. The Muckleburn of Stennis, this is the one where the thermal conductivity of the ground is a lot less than the other drills. So we're restricted to 7.1 metres depth of cover. So our depth of cover underneath the stream is only 4.4 metres. But again, we're in solid rock. You can see the assumed top of bedrock line there. And there's quite a sensitive environmental area across the length of the Stennis burn, which is why we've extended the length of the drill to 157 metres to stay out of the environmentally sensitive area. The Little Burn, now this is the only bore where you can see we just kiss the top of bedrock here. So the majority of this bore is going to be drilled in the clays and sands and silts and gravels staying above the bedrock. So we've got 7.5 metres depth of cover underneath the stream there, and it's 147 metres long. The A964 is just over 100 metres long, 102 metres long, and there's a few services in the ground there. Water, BT, there's a drain and another water pipeline on the other side. So these have all been trial holed. So we know what depth they're at, and we know what our depth of cover is beneath them. The bush, the inlet, the sea loch, this one's the longest of the onshore drills, 262 metres long. But again, you can see bedrock is pretty much at surface across the estuary there. So we've got plenty of depth of cover in solid bedrock. The 965, the road's up on a bit of an embankment. So although we're shallower below entry and exit point on that one to keep the 10 metres depth of cover below the road embankment, we're still able to get plenty of depth of cover into the bedrock. There's a couple of overhead lines there. You can see one out here and one here. And what we've done with the design of this bore is we've put the HDD in at sufficient depth that if at some time in the future they want to underground these lines, they've still got room to do so and stay above the HDD bore. So we've pushed that one out to 127 metres to accommodate any potential future works. And the last one is the Burn of Sunnerdy. You can see all the other services that are in the road here. Again, there's a sensitive environmental habit at the start point that we're staying well below. And then we've got some comms, some water, some high voltage BT. There's one unknown in there that we picked up when we were doing the trial holes, and a couple of 11 kV cables. So that's 243 metres long to stay underneath this sensitive habitat at one end, and all the existing utilities at the other. How are we doing for time?
Just gone up to 8 o'clock,
About 50 minutes.
about an hour.
Okay, so I've got some slides here of some of the other interesting jobs we've done. This one's the Current Narrows at Fort William, Loch Linney. Looking across, you can see the ferry here, and looking across at the lighthouse on the far side at the Current Narrows. SSE had 3 cables lying on the bed of the sea lock there, but as the tide comes in and goes out, they move those cables slightly and wear them away. So every 5 to 8 years they needed replacing. So we've now drilled them in 20 metres below the seabed, again in solid rock, for very similar reasons that we're drilling the cables at Warebeth, get them out of the tidal stream and protected in solid rock. And I believe they're now looking at putting an electric ferry on that crossing route because they have a reliable power supply to it now. These are a couple of fibre optic landfalls we did on the Kent coast. These are 2.1 kilometres long, 2,170 metres was the first one, and the second one was 2,300 metres. So 2.3 kilometres out to sea. They're the longest single drills done in the UK.
So what was that?
2.3 kilometres. There's a project on the cards at the moment that's 4.5 kilometres long. Now that's a long way to drill, because if you remember, we started off the presentation saying we oriented the drill bit in the direction we wanted to drill by rotating the string from all the way at the surface. Now, if you've got 4.5 kilometres of pipe in the ground and you put one turn in at surface, you might not get any movement in the drill pipe at all. All you're doing is putting torsion in the pipe. And then, of course, it all lets go and it all spins out and you lose it all. So once you start to drill beyond about 2.5 kilometres, orienting the drill head from the rig site gets very difficult. So what we're looking at to drill 4.5 kilometres, and the longest drill in the world, I think, was just over 5 kilometres when they built the new Hong Kong airport. And they drilled with 2 rigs, one from either end, and they drilled under the seabed and they met in the middle and then chased one out to make one complete job. So that's the kind of accuracy we're talking about being able to achieve now. The landfalls on the south coast went so well, the client took us across to Holland and had us drill underneath the Koningsdijk, the King's Dyke, one of the major flood protection barriers, and out to sea. So you can imagine the hoops we had to jump through to get permission to drill that. The stories of the little fellow with his finger in the dike don't come close. But yeah, nice job. Just over 2 kilometres, that drill, 2,085 metres. This was a job we did on the River Dee at the steelworks, Tata Steelworks. And you can see there's the 2 drills are the red lines here. They're replacing an old Victorian brick-built, hand-built cable water tunnel that ran under the River Dee there. These lines are all gas lines, high voltage power cables, sewer lines that we had to be careful of. But the striking thing about this job was the amount of contaminated land. We started off in a landfill site that we isolated with sheet piling. There was an old soda ash facility that dumped sulfuric acid on the ground here on the southern bank. On the north bank, there's a leach-shaped lagoon that we drilled underneath that was associated with the old Hawarden mine works. And then where we came out of the ground, these are old railway yards with a lot of asbestos and oil contamination in the ground. So again, drilling underneath it avoided all that. Another picture there, that's the same job. This one's Cork Harbour. We drilled 2 parallel shots over 1 kilometre long across Cork Harbour. There was a slight horizontal shift out under the middle of the harbour to get the exit drills lined up. And again, accuracy was very important. We had a basketball court to aim for at exit point. It doesn't look much like a basketball court there, but that was all refurbished at the end of the job. And then the pipeline was welded up in a field nearly 2 kilometres away and pulled down these narrow country roads for pullback. The first shot, we had a stake in the ground that we were aiming for, and we were about 20 centimetres to the right-hand side of the stake on punch out. And the second shot, we moved across and we missed that one to the left by about 18 centimetres. And one of the Irish water engineers said to me, you know, were you happy with that kind of guidance accuracy? And I had to say, I've been in pubs in Cork where the darts players don't have that kind of. So to be able to hit them from over a kilometre away, I thought we were doing pretty well. Those two pictures actually you've already seen. That's the major landfalls on the Caithness coast. Just to give you a little bit of an idea, there's some seals hauled out while we're drilling underneath them. So there's very little impact.
It's getting a back massage.
Yeah. As well as cable landfalls, we've put a lot of outfalls in for Scottish Water and for private industries, distilleries, pig abattoirs, paper mills. It's a very similar process. This one is for the Caledonian Cheese Dairy in Stranraer. There's an outfit that goes out at Port Patrick. You can see the rig site here split up. That's quite a steep slope. So we've got the rig on the slope and the fluid system up at the top of the hill. And just to finish up, a couple of the more esoteric applications for HDD technology. We talked about avoiding contaminated land, but there's a lot of work being done, more so in the United States, where groundwater is much more of a potable resource than it is here, for cleaning up contamination, pollution plumes. When pollution percolates down through the ground and hits the water table, it migrates off-site in a long, thin plume. So if you can chase that plume with a horizontal well rather than having to put in tens or hundreds of vertical wells, you can get much more coverage with your well screen. Whether you're pumping and treating, trying to pull that contaminant plume out of the ground, whether you're pumping air in to try and volatilize the plume and dissipate it, or whether you're pumping in a reagent to try and deal with the plume. There's quite a bit of contaminated land remediation being done with horizontal wells. Water abstraction is another application. We've drilled a bore underneath the Thames from Beckton Sewage Treatment Works. You probably know London is short of water pretty much every year. Thames flows through it, but it's full of suspended solids. But by drilling a bore 30 metres below the bed of the River Thames, we could pull water down and filter it out through the naturally sand and gravels on the riverbed. And the water coming up out of the well was 4 times cleaner than the legal requirement for tap water in London. So that's an application that's being used quite a bit. There's a number of desalination plants island communities is very popular with, but in the Middle East and Southern Europe, there's a number of these bores being drilled out from the beaches to pull seawater into the wells for desalination. Ground source heat loops is another application. And marine wreck recovery. Directional drilling has been used to drill underneath marine wrecks and pull cables through that they can then use to lift wrecks off the seabed. So another interesting application. And cathodic protection. This picture shows steel tanks. You might be aware when steel tanks are installed, they have sacrificial anodes put underneath them that rust preferentially to the steel tanks. But once that anode is gone, the tank starts to rust. But using directional drilling, you can replace those anodes without disturbing the tank operations. And we've done something similar with freezer pipes underneath cold storage rooms that failed or got blocked up. We were able to drill under them and replace the freezer systems. So,
What about bank vaults?
bank vaults, yes. Yeah, we could certainly drill into a bank vault for you.
Great. Thank you, Richard.
Absolutely fascinating. Any questions from anybody? We haven't covered as well. So I've got one to kick. Oh, I'll jump in first. There you go. In terms of the material you're seeing in the tailings that come back, can you describe what size they are?
So we looked at the picture of the recycling unit there, and it takes off a coarse fraction in the first screen. So that's kind of gravelly, small gravel-sized pieces. Okay. The next shaker down takes off a gradually finer material, so sand, coarse sand, fine sand, and the centrifuge at the far end, it's clay coming out of that. So we take a range of material. It's related to the drill bit and the ground you're drilling through. The size of the teeth on the drill bit dictate the size of the chips that are going to be produced. And the faster you can flush them out of the ground, the less abrasion they suffer on the way up the annulus. So we're getting pretty clean material out because it's a high percentage of it is coming out in reasonable sized chips.
Thank you. So then Gareth?
So at Warebeth, when you punch out into the seabed and you get that mix of bentonite and seawater, how do you manage that? You know, is it going to be bentonite all? Sorry, once you're finished, is it all going to be bentonite, or how do you manage that?
So before we punch out onto the seabed, we circulate all the cuttings out, and we'll run 1 or 2 wiper trips to get as much of the solid fraction out of the bore. So we've got pretty clean fluid to finally punch out onto the seabed. When we punch out, there will be some bentonite gets pumped out into the sea, but it flocculates and suspends itself. You can see the picture there of the job at Maygen with the drilling assembly sticking out of the ground, and you could see the kelp forest all around it. It wasn't, covered in drilling fluid or material by any means. As I say, it's clay in a freshwater suspension, so it's just.
And it's designed to be denser than water anyway, isn't it?
It is denser than water.
So it's going to sit in the bore rather than running.
Yeah, yes. What's left in the bore will stay in the bore. What will happen is that we lose it. It's like a U-tube, so we're slightly above seabed at entry point. So we'll lose it at entry point down to sea level, but it'll sit within the bore. Yeah.
So then do you backfill the rest of it so that you've still got the bentonite around the cable? Like once it's cured, or? Yes,
yeah. Once the bentonite that's in the bore has gelled up, we can fill up the top end like a 2-stage cement job. But we have to let the stuff that's in there gel up and take some load first before we fill the top end.
Thank you.
Gareth?
Yeah, so stone and aggregates is a kind of very precious material in Orkney. We've had a history of sourcing them from different places. Is there a use for the cuttings that come out of this? Is there a purpose that they can be used for?
Yeah, so the company that are taking them away on previous jobs that we've done on Orkney, they've used them as capping material for the landfill site. Material only becomes waste when it leaves your site. If you can use it on your project, it's not a waste. So we often use it in landscaping, we use it as bedding material for open cut trenching areas, we use it in reinstatement. Yes, it absolutely has a use if somebody can find a use for it. But once it leaves site, then it becomes a waste product, and you have to get special licenses to reuse it. Then, so there is a process to go through. There's nothing to stop its use. It absolutely has an application.
To avoid landfill tax by using it on site. So as it goes on. Where go? North first, and then
Thank you.
No.
Timelines wise, so for example, for Warebeth, you mentioned the topographic surveys and everything. How much time is the lead up, the design phase, and then also how much time do you take in actually doing the drilling?
So the design phase, when did I first come and see you again? It's probably about 18 months ago. We weren't in control of the topographic surveying or the site investigation or the existing utility trial holing on this one. So we were reliant on other companies performing that work. But it's job specific. If you're drilling under a railway, I can tell you right now it's going to take you at least 6 months to get a consent from Network Rail. Transport Scotland, they used to be a bit better than that. They're probably a little bit worse now. But this one's probably been in the design stage for 18 months, I would say. In terms of programme for...
not the whole picture.
None of them have got hats they want to hang on a peg.
We're looking at September.
September?
Yeah. Mid-September.
September.
Thank you.
We're a little behind programme. There were some delays at the start of the job. The drilling has gone very smoothly. There's been a couple of equipment issues that have delayed us a little bit, but
Thank you.
September.
I don't even know. I'll just approach Stuart's dad and see.
How do you work on earth movement geographically? Earth moves all the time. How do you manage that?
So do you mean once we've got the pipeline in?
You've got the pipeline and you get a tremor.
Yeah.
Right? How do you compensate for that?
Okay, so the vast majority of ducts and pipelines that we put in these days are polyethylene, and they're extraordinarily good at handling tremors, rifts, shifts, earthquakes. You'll find in Asia, particularly Indonesia and Japan, they're specified specifically for installation in earthquake zones because I'm not saying they never rupture, it depends on the size of the earthquake, but if you look at the alternatives, clayware, ductile iron, steel, PVC, they're far more brittle than polyethylene. If you've got a water pipe or a gas pipe and they need to do some work on it, they'll squeeze it off. They'll just get a clamp and they'll squeeze the pipe and stop the flow. They'll do the work on the bit that they need to repair. Yeah. They take the clamp off and it'll just spring back into shape. So the way the ducts and pipelines are installed isn't so much a function of dealing with.
So it's got a good flexibility.
Yeah.
For earth tremors. No?
Yeah.
Up here we're not bad, but there is other places.
Yeah,
you've got on.
And when we join them, as we saw, we butt fusion weld them.
Yeah.
So it's not a push fit joint. It's not a threaded joint. It's not a mechanical joint. It's welded into one single piece. So that joint isn't going to pull apart. You're not going to get tree roots working their way into it. It's not going to vibrate loose from traffic or train traffic over it. It's a single piece of plastic from one end to the other.
So it takes subsidence and that.
Yeah, it deals with subsidence really, really well.
Okay.
Yeah, okay. Well, it's a slightly flippant question, really. I think you're not going deep enough to discover anything interesting that's unexpected, like lithium or platinum or something like that, or gold.
No. The boys always say, we're watching the Shakers. We're drilling down at Moffat at the moment, where people panhandle for gold in the streams down there. And we've told the mud man that that's the case, and he's watching that mud. But no, it's such small volumes of material relatively that are coming out of the ground. You know, one of the advantages again of HDD over tunnelling is they take out the whole bore at once. So if they have problems with ground stability or come across unexpected material, now they've got a big bore to deal with. Because we drill a small pilot hole to start with, small fluid volumes, small volumes of material being removed from the bore, we can deal with any unexpected, if we hit fissures or caves, which we often do in limestone or chalk soluble ground conditions, or fractures in fault zones. Can cause problems. But if there's a deflection in the bore, we'll see it on the real-time guidance system, or we'll see changes in the drilling fluid circulation rates. We'll lose circulation and tell us that there's something wrong, or the rate at which we're drilling. It might slow down or speed up depending on what ground we're drilling through. But in terms of mineral exploration, the South Africans have done some work using horizontal directional drilling for one of the issues they have in their mining systems, especially the coal mining, Sasol. They use these long wall mining systems, and they're excellent rotating drums with big tungsten carbide teeth on that tear the coal out. But there's a lot in South Africa of igneous intrusions in the ground. And if the teeth run into one of these igneous intrusions, you know, the machine takes weeks to repair. So what they've been doing is setting up an HDD unit on surface and drilling out in directions and trying to locate where these igneous intrusive seams are below the surface and map them so that they can plan their longwall mining a bit better. So there is an application there for geotechnical evaluation, but I've not heard of it being used for mineral exploitation, I'm afraid.
What's the technology for measuring where the end is from 2 kilometres away?
Once we've popped out onto the seabed?
No, before you pop out, you know where it is within 20 centimetres, but how do you know that?
Okay, so the guidance systems we use, the guidance system we're using here is a ring laser gyro. So if you think of it as a circle, and there's a laser fires a light beam into the circle and it splits it, and those two beams travel round the fibre optic and back where they started from. If you haven't moved that circle, both those light beams will get back to the start point or the end point together. If between firing that laser and receiving that laser, the circle has rotated slightly, one of those beams is going to get back to your collector point slightly before the other one. So you can tell what orientation changes has been made between firing that laser and receiving that laser. If you set up 3 of these ring layers at 90 degrees to each other, so you've got one in a vertical plane, one in a horizontal plane, one in the third plane, you can tell pretty much exactly where you are at any point. You reference it at surface, you tell it this is your inclination and this is your azimuth. You drill 10 metres, you fire that laser, it'll tell you whether it's changed 0.04 of a degree is the accuracy in tolerance. So every 0.04 of a degree in inclination or azimuth, 0.01 of a degree in azimuth, it'll tell you what change has been made in the direction. So there is a tolerance of 0.04 of a degree. 0.04 of a degree, I think, is azimuth, and 0.01 of a degree in inclination. No, That's magnetic tools.
Yeah, yeah.
They're both the ring laser is 0.01 in vertical and horizontal plane. So there is a tolerance there. So the further you drill, the further apart you could potentially be. But after a kilometre, you'll be about plus or minus 5 or 6 centimetres. Statistically, those errors will plot on a bell curve. So you're actually going to be a lot tighter in than that, plus 5 or 6 centimetres.
So
Now, knowing exactly where you are and exactly where you want to be doesn't necessarily mean you can drill between those 2 points, because if you're drilling through bedded material like you can see in the cores, the ground's trying to push you off all the time. So, as I say, if we're hitting hard material or soft material, we're constantly trying to drill back to the centre line, to the planned tangent. But yeah, we know exactly where we are within a few centimetres and exactly where we want to be. Targets, sometimes we have really tight targets when we're trying to drill between a high pressure gas main and a high voltage cable, and somebody's foundation of their house. You need to be very accurate. Sometimes they just go, look, just get across the river and come up in that field. Then it's a bit of a quicker job, a bit cheaper.
Yes, sounds based on black magic, that bit, doesn't it, Rachel? Gareth, did you have another one?
Yeah, so are you able to drill anywhere? Do you have any surface restrictions that you can't drill under? Is there any no-go areas?
Legally, we don't drill under property without a consent, and agreeing a way leave and an easement. We don't drill under houses or buildings that there's.
Ever, or just without agreement?
Yeah, you could get agreement, I'm sure, but why would you? There's always an alternative route. We have drilled under buildings, but we would push back on that. In terms of ground conditions, again, as we say, if you can't maintain circulation and flush the drill cuttings out of the ground, you haven't got a hole. So if you're drilling in very porous, very permeable material like cobbles or boulders, imagine trying to dig a hole in a bucket of marbles. It doesn't happen. It's all going to fall in on you, and all your drilling fluid disappears into the formation. So there are ground conditions where we would say, no, the stuff we can do, we can set surface casing sometimes if it's not too deep. We can try and grout it up with surface grouting. Those jobs are probably better done by a tunnelling system than an HDD system.
So as a follow-up, at the start you outlined a lot of advantages of HTD and stuff like that, and I think this job, is it the third job that we've had in Orkney? The Shattonsea water pipe,
Fourth, two aquamarine ones.
The EMEC one, and then now.
Yeah.
Looking forward, we've got a lot of cables and things that are likely to come into our existence in the future. So this is going to be quite. So, what is the business case for Orkney? Actually, we think of the Faroe Islands, and they actually bought a tunnelling machine to allow them to tunnel between the islands and join their islands together, and that collapsed the cost to make it affordable. And they've got that roundabout under the sea and all that kind of stuff. Is it foreseeable that it would ever be viable or sensible for a place like Orkney, where there's a lot of cabling, and particularly marine cabling, linking islands that needs to be done, that we could strategically invest in an HDD unit and have it based here and build a team that could do it, so that we could be chipping away at putting enduring infrastructure in, which would have all the advantages that you outlined?
So you need continuity of work to gain the expertise necessary to run a big operation. You also need a variety of rigs. We're using a 500-ton rig at Warebeth. We're going to be using a 50-ton rig for the onshore drills. If the onshore drills were longer we might want a 100-ton rig or a 250-ton rig. If they were shorter and staying above bedrock, we might be wanting a 30-ton or a 20-ton rig. So one of the issues you're going to have is deciding what size rig to start with. And the second is continuity of work. How do you keep that rig working? Because if it's not working, it's costing you money. The guys that are running it, if they're not out drilling, they're going to be away doing something else. So those are the issues I think you're going to have with. If there's enough work for it, as obviously there is for a tunnelling machine in the Faroe Islands, absolutely, I don't see why not. I mean, we had 3 school groups from Stromness Academy out on a grand tour this afternoon, which is why my throat's starting to give up. But there was certainly some interest there in what we were doing. And some of the guys that are doing engineering, mechanical engineering, STEM subjects, be more than happy to hear from them if they're looking for a career in drilling HSE.
So just if I just so from an OREF point of view, one of the things we constantly try and do is think about our future planning.
Mm-hmm.
So we're just engaged with a process with NISO and with SSE on the modelling side at the moment, where we're working with those organisations to imagine what our future grid network might need to be. And I'm just thinking, if you think of all of the water crossings, the road crossings, all of the things that might need a drilling solution, or where that be landfalls, it would be an interesting tally to say in the next 20 years. And just in the top of my head, I'm thinking that might come to certainly over 100, and maybe, and if you had that technology, would it start to transform how we dealt with because you said overhead wires could be put underground if you've got the solution. So maybe we could come back to Azoref and while these guys are up, get them out for a couple of beers one night and then kind of do some maths and see what that looks like.
Absolutely, for the few beers.
A couple of numerical questions there. You said about the different sizes of the rigs. But what's the size of the bore you're going to be doing on land versus the size of the bore at Warebeth?
So it's a 26-inch bore on land, and it's a 36-inch bore for the landfall.
And is the difference in the size of the rig driven by the diameter or the length of the drive, or a combination of both?
Combination of both and the ground conditions.
Right.
Do we need rock drilling tools, or is it soft enough to drill with a jetting assembly?
Okay. And roughly the power consumption of the 1A Warebeth, I'm just curious what size.
In terms of diesel consumption?
Yeah, kilowatt or whatever units you work in.
Yeah, we're around a cube, 1,500 litres per shift.
Of diesel?
Yeah,
Okay.
yeah.
And that's running?
That's 12-hour shift.
12-hour shift,
Yeah.
Okay. And does basically the diesel's on at flat rate, or does it bite when you're drilling hard? Or just
Yeah, we consume more the bigger the hole that we're cutting, or the more that the rig's working.
Yeah, just curious to get some sort of scale of what's needed, because one of the challenges we have with renewables is often people not appreciating how much energy it takes in diesel compared to what it would take to do renewables.
Yeah, there are electric rigs coming out on the market now as well. It's very early stages, but there's going to be a big 300-ton rig running off the grid next year, so that'll be pretty interesting.
And once again, in terms of the power consumption on the site, what I saw were about 3 main uses. There was the drill rig, there was the tables for agitating, and then the general pumping of the materials around. So I take it the tables are not particularly energy intensive because there's a pump to pump the fluid up and the agitation of the table and cycling.
Well, we have a 500 kVA generator that pretty much runs the whole site.
Okay, yeah.
Of which we probably use about 350 kVA, so we have a bit to play with.
Yeah, curious. Thank you.
Just to build on that question, which side, if you're doing it that you're sort of pushing and then pulling, which side uses more energy?
The Well, the pushing side, if we're doing like conventional HDD crossings with the pull reaming, there'll be a much smaller setup on that side to the rig side.
Oh, of course, sorry, that makes sense, because,
Yeah.
Well,
But just one thing, maybe to drill these holes, 1,200 metre holes, 36-inch hole, probably takes about 2 months to do each hole, 24 hours. To actually push the pipe in to install it will probably only take about 6 hours. So obviously all the work is in making the hole. Actually installing the pipe is the touch wood process.
So you just mentioned there 24 hours. Does every 26-inch hole have to have 24 hours working?
No, it's ground conditions, it's length, it's
So say at Orkney Rock, what would be the smallest hole that wouldn't have to need 24 hours conditions?
well, length. When you start getting over a kilometre, any size hole, you really want to start 24-hour operations, but especially beyond the pilot hole.
Yeah.
So when you generate a lot more cuttings, so like the 12 1/4 pilot hole, so 12 1/4 pilot hole, then 26-inch ream. The 26-inch ream, we generate 2.5 times the capacity of cuttings that we do on a pilot hole. So when you're running that in a single shift, try and carry all that cuttings out, and then you stop for 12 hours, you're just fighting it again the next day. So really when you start reaming beyond the pilot hole in rock over long distances, you want to, very advantageous and less risk for us to run 24 hours.
Interesting. Any more for any more? Because we've got experts in the room here, and I think we're very privileged to have been able to get this depth of answers. So, even go on.
2 questions with no
The floor.
What's the shortest distance you've ever done from one HDD to the next HDD? So like almost from the exit of one to the entry of the next.
Up and then again.
Many, just continuous. Yeah.
Okay,
Yeah,
interesting.
we do a lot of what we call line work. So for a small diameter pipe, 180mm pipe, for example, if we've got a couple of kilometres to do down the hard shoulder of a motorway, we'll set the rig up, we'll drill 100 metres, we'll pull in 100 metres of pipe off a coil trailer, we'll spin the rig round, we'll drill 100 metres in the other direction, pull 100 metres in, tie them in the pit, and then move the rig up 200 metres and repeat the process the next day.
Because we can generally drill it a lot quicker than what they can open cut it.
Okay, so
interesting.
it depends on what it is you're
Right.
putting in. So like a electrical cable, a larger electrical cable is going to have a maybe more of an issue in terms of bend. Would that be right? Than your fibre optic?
Yeah. I mean, an 11 kV cable will go in a 180 duct. These are 220 kVs, which is why they're needing, and there's 3 phases, so each phase is going in a 200mm duct, and those ducts are in a duct bundle rather than just putting one duct in and then pulling a cable or running a cable through. So it depends on the size of the cable.
So if I hear from a developer, this isn't an Orkney by the way, but if I hear from a developer that they can't use a horizontal, sorry, I'm just going to HDD because I can't see. They can't use HDD because they're using it very close. So they can't use it to go under a road because they're using it to go under an archaeological site nearby. I should probably challenge that a bit more. Do you think?
I'd have to have a look at it because that happens all the time. We've got a river to cross and then they go out and they do the trial holding, especially for angling water. There's a lot of Roman ruins in the angling water area. They'll be digging a trial hole and go, oh, we found a mosaic or we found a piece of clayware or something. The archaeologists just rope it all off. So we end up drilling a longer bore to do the river crossing or the road crossing and the archaeological site in one go. You need room to string the pipe out at exit site. So if it's 180 or smaller, it'll come on a pipe coil trailer, so you only need room to park the trailer at exit point.
Yeah, this was much larger. It was for an offshore. Okay, so yeah, much larger than that. So
I need to know a bit more about the job.
The second question was by putting in the HDD under the seabed instead of having the cable on the sea, does that then mean it's technically not a subsea cable? And does that, I know it's a bit weird, but getting insurance for subsea cables is so difficult because it's difficult to repair them or replace them when they break. But if you've got it through a HDD duct, doesn't that make it easier to repair or replace if there is something going?
Well, certainly that example that I showed you of the Coronaros where they'd taken the cables off the seabed, again, one of the drivers for that is they were going to the cable manufacturers and saying, you know, we need 500 metres of marine cable.
Okay.
And they're going, we'll get in the queue. All my other customers are ordering subsea marine cable in hundreds of kilometres at a time. They're just not able to get marine cable. But by drilling, now that was land to land, but across a sea lock, once the duct's in the ground, they just used a standard onshore cable. You know, they just rolled it out in a drum from the local store in Fort William and pulled it in. So it alleviated those supply chain issues. When you're drilling from onshore to a subsea exit, whether that qualifies as a yes, you could put a conventional cable in there, but then you've got the transition joint bay between the conventional cable and the marine cable on the seabed in 15 metres of water. So there'd certainly be some pushback from the engineers on that one, I would say. It's worth exploring.
So if it's less than 2.5 kilometres distance, it might be worth exploring maybe, just based on what you were saying earlier about your potential limits at the moment in distance.
Yes, for a single shot, but you know, for an intersect drill that meets in the middle, absolutely that can be done up to 5 kilometres.
And the reason I ask it is because it causes an issue for insurance if you're connected on a subsea cable. So
interesting.
Thank you very much.
The Shapinsay water pipe, that was close to 2 kilometres.
The beauty, of course, as well, if they don't need to grout the cable within the pipe, there's potential 20, 30 years down to pull that cable out and replace it as well.
Well, that's actually a question. So would you do that much with not having that grout in it? Or?
I've done a couple where we've had to replace them, but they weren't grouted in, of course.
Okay.
But there's different kinds of grouts. There's the bentonite, which is a weak grout that we would use as the drilling fluid. That's in there anyway. As I say, there's the cementitious grout. So if we're drilling under a railway, they'll often ask us to put a cementitious load-bearing grout in the annulus. There's the thermally conductive grouts that's specially designed to wick the heat away from the cable. And there's gels that don't have a cementitious element or a grout element, and they're designed to go inside the cable duct, but act to wick the heat away, to transfer the heat away from the cable, but they don't, you know, they stay gelatinous and can be flushed out of the bore if the cable needs to be replaced.
And presumably then replaced.
And pull a new cable in and replace the gel. Yeah. Now I've not pulled one of those cables with the gel around it. I don't know if you have.
It's not round the gel, but in an open-ended pipe. Yeah, back in the US we did replace one a few years ago, but not within the gel one.
Well, Dave, go on. Last point.
I was just going to anticipate you and say a lot of ex-engineers and current engineers in the room, and I want to express my appreciation of your openness where you shared what might be regarded as trade secrets. And I just loved it.
Well, we'll do it that way. I was just going to draw us to a close, say, thank you very much indeed for all that and the technical information. We're in the Charles Clouston building, part of the campus. The other buildings are at Rendell building. And it was Charles Clouston was the geologist, wasn't he? Yeah. And so Charles Clouston collected stone samples around. He did a huge amount of geology in this area. And I can hear that faint whining noise of him spinning up in his grave at the moment about the sheer scale of what you're able to do now, which simply would be breathtaking to people who, frankly, did some of the original geology. If you get a chance while you're here, if you go to Stromness Museum, there's actually a fossil in the museum collected by Clouston, which actually features in The Origin of Species by Charles Darwin. And so the whole issue of geological interpretation is really very, very germane to what goes on here. So seeing this new piece of technology, comparatively new technology deployed in this innovative way to deliver a new industry is really fascinating. So thanks, Trenchless, for tonight. Thanks, Trenchless, for the work you're all doing to make this all happen. We really appreciate it. If people have got ideas for other technical presentations at some stage, then we'd be delighted to find ways to host them. This will be put up on the ORF website, courtesy of Mike and Angus's great work, who put the cameras and stuff up for this. It'll be available later on. So if you know young people who want to be inspired for a new industry and get a job in this, get them to watch the damn video. That'll do. Thank you, Steve, for coming. Appreciate it. Oh, yes.